How are the bits and bytes doing today? Excellent. It sounds like we've got a whole round trip all the way through the computer, through the preamp, all the way out to the internet, and all the way back to another computer on my network. So if I'm not live for anyone else, at least it's working for me. Sometimes that's all you can ask for. We will give it one more minute here before I start. Hello, my name's Ben. My amateur radio call sign is Alpha Bravo 4 Echo November, and this is Stray Capacitance. I hope everyone is having a great day. The world is a little weird right now, so I decided to, rather than doing something any more responsible, I figured I'd put together a quick stream and talk about some things I've been working on, some random projects, and where I got to with the Logitech Trackball sensor reverse engineering project, which I'm working on. I've got a cup of tea I can show you. It is just lovely. Nice cup of Rubio's no caffeine tea. Last thing I need in life is more jitters. With some wonderful honey in it. A nice complement to an overcast and hopefully calm day. If anyone actually ever runs into this or watches this, I hope you're doing great. This is obviously only my second stream. And mostly what I've been focused on so far is reverse engineering these sensors for the Logitech trackballs. That's been a fun little project, and I've made some more progress off stream, so I thought I would share that, but also just kind of talk about some other projects that I've been working on. I'm a long-time fan of 3D printing and very much enjoy the hobby. I joke with several friends that my hobby is more 3D printers than 3D printing. I'm never quite happy with the printer I've got. I'm often building one or working on one. And so I've got some of that going on here that I wanted to talk about just a little bit. My current printer is a Core XY printer that has been kind of a workhorse for me. I built it out of scrap parts after several earlier printers. It's my 2, 3, 4, fifth printer, I think. All of which have been, the first one was kit built, and then all the rest have been just DIYs. Sometimes using a someone else's model, like the Wilson. Sometimes riffing on a common idea like a Delta or a Core XY, where there's a lot of kind of knowledge in the space and a lot of people doing similar things. So this one is a Core XY printer, and I've been very happy with it. As I said, it's kind of just was built at my constraints when I built it were mostly just what did I have on hand. And so as such, it's always been a little bit of a kit bash, a little bit of a compromise printer, but I've been very pleased with it on the whole. It's got a couple difficulties right now that I'm still diagnosing, but one of the things that's been on my list for a long time, I use belts, the kind of standard G2 8mm belts, to drive the carriage around. and those have worked very well. I'm running them over smooth bearings in a couple of places. And so one of my upgrades that I've got planned are a couple parts like this. And we'll see how autofocus does with me holding this up. But the the belts currently run over smooth bearings on the printer, and this would give them proper idler pulleys with teeth. So that would hopefully eliminate a little bit of lash in the printer. Print quality isn't terrible, but there are certainly some artifacts I'm working out. And unfortunately, even after all these years of 3D printing, I'm not the best calibrator. I tend to get bored with calibration once the print quality gets to a certain point. And so I've never done a good job of chasing down all the problems. So I'm working on doing that more. And some of the problems seem kind of mysterious. I always expect I've got some temperature related issues or things like that, and they don't make any sense. You think you're printing too hot, so in proper debugging fashion, you try to make it worse by increasing the temperature, and it gets better. And for some reason, but it doesn't hold up. It doesn't continue to get better, or it'll get better for a week and then it'll get worse. I've probably got some airflow issues just due to where the printer is located. My office is fairly small and cramped, and I've got a lot of hobbies. So the amount of space I have to work in is somewhat limited. I should be keeping a closer eye on my audio levels. I'm sure I'm peaking a little too high. It's another area where I hope to improve. Anyway, so I've got several pieces to this upgrade. There's these parts, of which there are two, that are just kind of idler blocks. They will go at the front of the printer, and both the X and Y or A and B belts will run through them. And this should take up a little bit of vibration as the toothed belt runs over the smooth at the moment bearings. So designed and printed these. I'm using natural PETG for these. That's what I've used for most of the printer, and I've been very happy with that. As a side effect and a completely uninteresting part, in the current design, those same idler blocks are also what hold my linear rod for the Y axis. So I took a design that I use in another part of the printer and printed off a few of these to hold that Y rod. And then there's also new Y carriages. So currently this is kind of the shape of the Y carriage, and there are two of these in roughly this orientation, with two rods running between them, and the X carriage runs on those rods on normal kind of LM8 UU linear bearings. And you can see here that the belts also run through here in these two holes, one on each. Two out of these four idlers, so there's two on each, right? These parts are identical. They are not even mirrors. They're the same part because you kind of rotate them 90 degrees like that to get the proper orientation for the printer. Two of these idlers will continue to be smooth because the belt will be running backwards when it gets to them with the smooth back side of the belt. So those will continue to be smooth bearings. But the other two, I didn't even show these, will run over these small, I believe they're 16 tooth idlers with bearings integrated. So I'm hoping that that helps me address some print quality issues. I'm not expecting a world of difference here, but it is something that I'm hoping to improve on as time goes on. So that's one project. Another thing I've been working on, it's still early spring here in the Midwest, and the weather's still fine, but not great. So it's a good time for radio amateurs to invest in antenna projects. And the ARRL came out with this book a few weeks ago. We'll see how the autofocus does with this. Ooh, nice yellow shift there. Oh well, so much for white balance. Overrated anyway. on strictly receiving antennas. And this is of a lot of interest to me. I also have an older edition of the tome that is the ARRL antenna book. And I'm in a very RF noisy environment. Right out my back window, which is the side of the house that my lab and office are oriented on, is there are some high tension lines. There's an electrical substation down the end of the street, and I suspect there are a lot of other noise sources in the area. I'm not far from a couple of transformers and other some such. So I believe I've got a lot of RF noise from a lot of different sources. And certainly when I put my radio and switch it to my vertical antenna, I get S9 noise on most bands. So I know you can't see this, but I'm just tuning around on 20 meters, and I'm S7 to S8. If I swap down to 40 meters, it's also around S7 for the noise level, which is nice and high. And that leads to difficulties doing several of the radio things I'm interested in at home. So I've gotten very interested in parks on the air, but I'm also interested in reducing the impact of that noise on my work at home. So both of these books talk about several different kinds of interesting antennas, but one that I thought would be interesting to possibly show, they have some interesting pictures of. And receiving loop antennas used to be very common. They were some of the first antennas, and they're much less in use now. Now people are much more interested in their transmit power, and receiving loop antennas, as you might guess from the name, are receive only. But they have some very nice advantages, and specifically they have fairly deep nulls. So there are a couple of different common loop antenna types, one of which is a electrostatically shielded loop out of the ARR antenna book there. And the circuit diagram for this is actually incredibly simple. It's just a loop of wire with a tuning capacitor across the end of it, and then a sense loop inside of it. That's L2 in that diagram that is not on screen. Nice work. So you often need a preamp with these. They're not very efficient and not very sensitive antennas, but they have deep nulls. They're reasonably directional, kind of in the same way that a dipole is directional, but because these are much smaller, they're kind of easier to focus. So I'm interested in building one of those. I actually have the materials on hand for the most part, but I just need some time to get down into the garage, and our garage is unheated, and as I said, it's kind of still early spring here. So that's a project that's still on the list. But the thing I've spent the most time working on recently is this trackball sensor. And so let's talk about the trackball sensor a little bit. I've learned some things since the last time I streamed about this, and I thought it'd be fun to kind of go over that. First thing I learned is that I had 3 of these trackball sensors, and I know you can't see that one, just from old trackballs that I'd salvaged. And it turns out one of them is bad. And I will give you a guess as to which of the 3 I selected for my initial experiments. You only get one guess, though. And if you guessed that it was the one that is bad, you would be completely correct. So I was very fortunate that I was talking about this project to a friend, and he happened to say that he had an M570 that he was not using. It was sitting in a closet, going completely unused. So I took the opportunity to thank him very much and borrowed it from him. And as soon as I got it home and started playing with it, and I should have noticed this with my own M570, which lives on my desk 100% of the time because it's one of the greatest pointing devices ever invented by man, or woman, or anyone. The LED on the motherboard with the setup I had was not behaving properly. Rather than going solid when it was turned on, it was blinking about once every 3 seconds, 2 or 3 seconds. And that was not what his was doing. And once I looked, that was not what mine was doing. So investigating a little further and of course doing the normal thing of swapping parts over, etc., I realized that the sensor was bad. So that was one interesting part. So the sensor with the black dot on the back of it is verboten, no longer useful. It's interesting that it does in fact respond over SPI to the microcontroller, but there is either a mismatch between the motherboard and the sensor, or the sensor is optically dead, but its internal electronics are okay, something along those lines. There's some circumstance that causes that sensor to not work, or at least not work like the other two that I have access to. So I learned that. That was very interesting. I also put some effort into my experimental setup here. And if you saw the earlier streams, you probably saw the giant bed of nails. Apologies, not the bed of nails. I've been calling this pinhead. This beautiful little kind of carriage for a PCB, and then these 3D printed arms with acupuncture needles on the end of them, and wires are crimped to the acupuncture needles, and that lets you take those off to a logic analyzer. So you can kind of probe points on the board and listen to various signals. And I was doing that, but of course I was interested in this tiny little 10-pin connector. Let me very quickly set up, duplicate, I actually have one of these small USB microscopes, and I'm going to quickly get to the point where I can show you it alongside the bench cam, because I think that would be neat. We'll do half and half. How's that? We're going to do this extremely haphazardly. Maximal haphazard. Alignment, what is that? Okay. Let me switch scenes here. Okay. Ah, of course it switched scenes as soon as I created one. I did not realize it would do that, but that's interesting. Good to know. This is some professional television here. So if I move the webcam in, and if the webcam chooses to update, or the microscope, I'm sorry. Why are you not updating? It's because let's just get rid of that one. Switch to studio mode here so I can actually make changes before you see. So I'm going to switch you, see only the bench cam, and that will let me hopefully play around here for a second without boring everyone. Aha, there we go. Transition. Like I said, professional internet television here. All the best. So this now is hopefully good. Okay. actually visible. So if I pan this to the right a little bit, probably too far, there we go. You can see the wonderful world of the tiny, tiny connector. And for reference, that there you're seeing is the end of the acupuncture needle. And the needle shaft is 1/4 millimeter. So there we go. I've got that on the right path now. So probing that little tiny connector was a bit of a chore. I was not having good luck with it. I was getting decent connections out of it, but they wouldn't be consistent. As you'd imagine, you move one needle, another gets bounced just a little bit, and that does not work out well. So I wound up taking the board out of this test fixture and realizing that on the bottom it had a programming header. And programming the 8-bit AVRs is actually done over SPI. So I soldered a couple of 4-pin 2.54, 0.1 inch headers to this, which they happen to be spaced perfectly for, which I'm 100% sure is for the benefit of Logitech and their programming headers and not for my benefit, but it worked out very nicely. So this gave me much more secure connections to the SPI bus. And I've got documentation about which pins are which. I need to type that up and put that into my repository, which I'll be showing you all here in a little bit. But that gave me a much, much better hold on solid signals. So what have we changed so far from last time? We've changed how we're getting the signals. We've got a known working sensor, and the other big change that kind of let things move forward for me, let me make sure that's reasonably secure. It is. If you see me connecting a red wire to a black wire here and a black wire to a red wire, and you're like, no, you fool. I am a fool, but I was a fool when I soldered these to the original battery connectors on the board. These colors are backwards. This is the negative, this is the positive. So that's when the mistake was made. Just one of those irritating things that you get wrong. So now I had a decent probe set up. It was time to revisit my tools. Last time I spoke some about the Analog Discovery 2, which is a very nice tool. And it does a little bit of every single thing you can possibly imagine. Let's use the microscope here real fast to double check my connection, because it would suck to not be hitting the pad. I am, but not very well. See if we can get a better probe on pad 6 there. Pad 6 is chip select for this this sensor, and so it is not exposed on the bottom side of the board. It is the only pin that I continue to need pinhead to probe. And that works probably okay. Is it? Is it really? Part of my problem here is that the microscope is too close. There we go. That looks like a connection, probably. We'll find out. Sorry, I was rambling about the Analog Discovery 2, which is a very nice tool, and it does a little bit of everything. It is a oscilloscope, but not a very fast one. It's a waveform generator. Again, not the world's fastest one. It can do power supplies, but can't provide too many milliamps and is limited to 5 volts, I believe. You may be able to get, I think there's an external power supply option, but I can't remember if that gives you up to 9 volts or if it just lets you draw more milliamps. It does a great number of things, and I'm still very glad that I bought it. But one limitation that I was running into was the speed of the logic analyzer. And if you've never run into it before, a logic analyzer is generally used for digital signals. An oscilloscope is great for kind of analyzing the analog domain, and you can certainly still use it with digital signals, and you may well want to because everything is analog at the end of the day. So if your digital signals aren't maybe as well formed as you'd like, or there's ringing on them, which is an analog feature, or something like that, then the oscilloscope is the right tool for that. But when you're looking to do things like protocol analysis, what you really want is a logic analyzer. And this was a case of the right tool for the job. So I had gotten into the Analog Discovery 2, and I had reached the limits of its capabilities. So I finally remembered and then finally found in my massive mess of an office that I had one of these little uh, these little uh, eBay Salier logic analyzer knockoffs. This has Salier on the sticker. It's not from Salier. I feel super bad about supporting a knockoff product, but this was also $10, and I don't need everything that their beautiful, more advanced logic analyzers do. And I'm also running under Linux, so I don't feel bad that I'm also, not stealing their software and running it with a product that's not theirs. I'm using SIGROC, which we'll talk about here in a minute. And this allowed me to actually capture the signals at the speed that they were happening. So my big lessons learned from last time, none of which are particularly, earth-shattering, and all of which I've learned before in my career, but hey, you know, you get to learn a lot of things many, many times. One is to make sure that the thing that you are analyzing actually works. Make sure you've got a working sample before you start digging into its behavior. So just kind of verify those base assumptions. Think about the little things that can go wrong, right? I had so many small connections that I couldn't get all of them to be reliable at the same time, and even if I could, any bump to my test bench was moving one of the pins around, and then I was having a 5 or 10 minute frustrating little expedition of trying to get all the pins back on the right pads. So look for a better solution. In this case, soldering some headers on the bottom of the motherboard gave me completely solid signals that I could use. And then right tool for the job. Don't get enamored of your tools. I was kind of in the mood to use the Analog Discovery 2, and it was a reasonably expensive bit of kit, $300, not insane for this space at all. But I assumed that that was going to be a better tool than the little $10 Salier knockoff from eBay. I was incorrect, and I was trying to make it do something it wasn't meant for, and it was just a poor approach all the way around. So once I got through all that nonsense, I was able to actually get things working. So let's talk about what we can see here. So this is PulseView. The actual underlying open source product is called SIGROC, and it's a command line tool, and it is incredibly powerful. PulseView is kind of the UI that runs over SIGROC and is also very powerful. It doesn't quite expose everything that SIGROC can do, but obviously UIs make things nicer. So I'm using the UI. In the past, pardon me, I've actually done a lot. I've written a few SIGROC plugins for another project that I may talk about at some point in the future. I was reverse engineering the radio protocol for a set of the Hallmark ornaments that kind of speak to each other, the little Charlie Brown ornaments that coordinate their song together. So you press a button on one, and the other four ornaments start playing along the same song with very good precision. So I was very interested in that, and I've done some work on that. I haven't finished that project. So, what is this? This trace here is me booting up the trackball motherboard with the trackball connected through the new reliable points that I've put in and with a working sensor and monitoring the conversations. So a couple things that are important to note here, and we'll talk about them as we get into things a little bit. The trackball is not the only sensor or not the only device on the SPI bus here. The radio that the trackball uses to communicate to the PC or to the USB dongle is also on the same bus. So, given that, we have to pay attention to the chip select line. If the chip select line is high, the processor isn't even talking to us. So we can see all this time here, the chip select line is high, and we're not being communicated with. And you can kind of see another window up here where it's clear there's more stuff going on the bus than conversations for us, right? So that's one thing we have to pay attention to. The and kind of the primary one. I also have a D1 line here. I thought there was something else that needed to be probed at the time. So these pins here are the actual logic pins that PulseView or SIGROC is monitoring. And I've given them the names of what they turned out to be. And to some degree, we determined this previously, and I talked about it a little bit in the last stream of I had just simply gone through the pins. That's not helpful. I can't remember where the navigation panes. There we go. Where the pins got traced back to the processor. Just kind of buzzing it out, or in a couple cases, following the trace back over the board the hard way. There was a little bit of like, it's only a 2-layer board. Luckily, a 4-layer board would be completely beyond my capabilities. But this allowed me to kind of track out what I thought the pins were. And in some cases, like pin 7 here, just kind of note what I saw going on with this. So I had suspicions about what was going on here. And that led to the labeling of these pins. And the way SIGROC and PulseView work is that the signals are just kind of the signals, and then you can layer in protocol analyzers on top of them. So you can come up here and say, I've got a SPI bus, an SPI bus. And when you bring that in, you configure it and you say, okay, where's the clock signal? Where's MISO? Where's MOSI? Where's the chip select? And then the various things that are important with SPI. Is the chip select active low? What's the clock polarity and the clock phase? Both of which are kind of discussed in that Wikipedia article that I showed last time, just talking about SPI as a protocol. 00 seems to be the most common and seems to be correct in this case. So that's why those are set that way. What's your word size? What's your bit order? And again, these seem to be very common. And then you get an additional decoder here. And we can zoom in here and see that, okay, So here chip select goes low. Put some cursors up here so we can talk for a second about that. There. So chip select goes low. Oh, there we go. Meaning that the processor wants to talk to us. Wonderful. And it starts waggling the clock line. And on those edges, and I believe it's on the rising edge, we sample master out, slave in, Mosey. And our nice SPY bus analysis here will turn that into data for us. So we can see that in this window here, we get the byte 0A. And at the same time, the byte that's coming out of the device, meso, right? Master in, slave out, is 0, 1. So we talked a little bit last time about how kind of you have to clock data in. The processor's in control of everything, and it has to clock data into the device to get anything back out. So 0, 1 is probably just the very first byte that was in its FIFO, its outgoing buffers, right? So the device doesn't know anything about what we want from it or anything yet. We're just going to give it commands and parameters for the most part. And as near as I can tell in SPY, these are frequently, but not 100% of the time, paired up. So really, this is a unit of work. 0A will wind up being the command, and B8 will wind up being the data associated with that. And a lot of times, this will be set register A to B8, something like that. And so these 2 bytes together make a unit of work, and then the next 2 bytes make a unit of work, and so on, and so on, and so on. So we've got a bunch of units of work here, and they are interesting, and of course we can zoom out to this level and kind of see how we're going. One thing that I saw quite a bit that I suspect to be true will be like here. Let's do like that. So here's the command 0B and the value 09. I think what happens a lot is that after the command is in, the device, the slave, knows what it can at least provide the current value for that register, right? So I believe in this case it's saying set register B to 9, right? The master out, slave in, the processor telling the device what to do. And the device is seeing, oh, you want B, well, my current value is 9. So this actually winds up being a no-op. But this whole section is the initialization of the device. You know, these sensors are, I'm sure, used in something else, and it doesn't come up in a known state. So maybe it was partially powered off and partially back on. The registers could be in any state. So we're going to go through and just set up everything that's important. And these, I don't really know what they all do, even slightly, actually. But they're almost certainly setting things like the resolution and the refresh period and all those different things for this device. So if we zoom out here, there's this whole block of initialization. And I believe, if I remember correctly, there were about 45 commands in here, something like that, command and data pairs that go into setting up the trackball sensor appropriately. And the only way I'm aware of to get into these, and again, you kind of see the pattern here of set register 21 to 4, but it's already 4. And then 4 gets echoed again on the next thing because the device doesn't have anything new to send you, right? It's getting bits in, it has to clock data out, but all it can do is send you what it's just set the data to, or the last byte that went out, or something like that. So, sorry, slight digression. So this is all initialization, and I have no way to really dig into this except to start fiddling with things. This is kind of interesting. You can see here, I'm sure sometimes there are reasons to do things in specific orders, but in a lot of cases, these registers are just being set in ascending order. So set register to B, set register to C, set register to D, to E, to F, 3, 0, 3, 1, 3, 2, 3, 3, and so on and so forth, right? It probably doesn't matter the exact order, but they chose to just go with ascending order, almost certainly just for convenience, right? And who doesn't like something that makes sense? So we set register 3C, we skip a bunch, set register 7.1, 7.3, 7.4, 7.5, 7.6. It wouldn't surprise me if 0.2 is kind of a general status register. And that set lower bit there suggests to me that maybe that's the turn your sensor on, get started bit, right? Again, I'm supposing a lot. But that is the initialization block. And actually there is another, if I zoom out here enough. Oh, I thought there was. No. You can see here initialization for something else on the bus, right? Our chip select is not low, so we're not listening. And luckily the Pulse View SPI decoder is smart enough to not decode this because we told it which chip select line we're listening to. So it's not giving us the data we don't need. So go through a bunch of initialization. Time passes. Time passes. Turn off our cursors there. And then we start getting to work. And there's a little bit more initialization. There's one more kind of set of packets that are odd out. 0870 and 0281. And again, 0281 was the one that I suspect might be the get yourself ready and turn yourself on. That is the last packet like that. After that, all of ours wind up looking like this, in that there are 5 bytes and then 3 bytes. Okay? And this sequence is always repeated. B3, B4, B5, B6, 80, 84, 85, and 80 again. What isn't constant are the response bytes. So it's important to note too that nothing else, there's no other conversations with the device at this point. So this 80 here, again, remember that this 00 is the response to this 85. But this 80 winds up being the first response byte on being the command that results, or the data that results in the first response byte on the next packet. And we see 80 here as well. So this is a response to this, and this on the next packet is the response to this. So we're getting 80, and we're getting something like 49 back out. And if we flip over to my notes, get rid of that. There we go. I went through a bunch of packets and analyzed a bunch of things, right? Because what else can you do? And so this is our pattern here. And I just started taking notes. So in the byte associated with B3, which again is a response to 80, right, from the previous packet, I've seen 39, 09, 79, 49, and C1, just looking through the trace. B4 appears to always be F1. So the result of B3 is always, or I'm sorry, 1F. The result of the B4 byte is always E0, The result of the B5 byte is always 1D, B6 is always E2. Then we send another 80, and again, this 80 can result in 839, 09, 19, 49, C1, and it always seems to match the B3 up here. So in this kind of unit of work, in this pole of the device, these two 80s, the one from previously and the one from now, seem to always match. Now, C1 here showed up when byte 1 and byte 2 here were not zeros. And 81 showed up when they were FB or FF as part of a moving capture. So the trace I've been showing you so far is just me booting up the device when it was paired to a computer. And so I didn't provide any input, I didn't do anything else. I just kind of wanted to see what was going on. And we can see like there's some network communication going on here because we know that the network transceiver is also on this SPI bus. So there's some of that going on there, but mostly we're seeing these polling events, and we can pick any of them, zoom in, and they appear to be more or less identical. 09, 09, 00, 00. Zoom back out, pick one at random. 09 is the first byte, 09 is the first byte of the second part, and 00 and 00 for the next two bytes. So that's interesting. We see our poll, right? We can, from this point, we can kind of get a sense of how the devices are communicating. And just for timing's sake, we can always zoom in, take a look and say, okay, so what's our time here? From the beginning of one to the beginning of the next, we're at about 7.8 milliseconds. Cool. So about every 8 milliseconds, the processor is polling the sensor. Interesting. So then let's provide it some data. And I've got this separated off in a different trace. And I didn't add in the SPI trace here. So we'll double check to make sure that it did something smart. But since I've named my signals well, it did a good job. So you can kind of see here we've just got normal kind of a pattern going on, right? Because it takes me a little bit after I start the trace to get ready. But about 500, 450 milliseconds in, it gets a little busier, yes? And you can see here, it's kind of interesting, huh? Okay, so our response to B3 instead of 09 is now 81. And we've got some data here in these bottom bytes of the second part of the poll. Okay. And then there's other traffic on the bus, which again, we know is the network. So what we're seeing here is it noticing that I'm moving the trackball sensor and responding to that. So 81, 81, 03, 00. The rest of these bytes still match what they did in a non-moving poll. So we can probably ignore these 4 response bytes. Go back over here and again randomly select one. 09, 09, 00, 00. And here, and all I'm doing here, I'm certainly no real reverse engineer, right? But you're looking for differences. You're providing some stimulus to the system and trying to see if you can figure out how it reacts. But here, it's kind of rare to see these little bursts of network activity right in there. Here, there's one here, there's one here. So those are 100 milliseconds apart, which is kind of a long time. It's certainly within the realm of human perception. So you wouldn't expect that the trackball would be able to be that laggy and feel nice, right? If we look here, here's some network activity. Here's some more network activity. So if we take a look at that, between these two network bursts, and if we assume that kind of these 3 bits of activity are all required for the network, right? Some kind of setup, maybe a transmission, maybe an acknowledgement, I'm guessing. But these are happening pretty much every packet from the trackball sensor. And these are 8 milliseconds apart, which is very fine. You know, that's close enough that at least I'm not a Twitch gamer and would never be able to distinguish 8 milliseconds of lag. Some days I'm lucky to get 15 minutes of lag noticeable. So we've got network activity. We're definitely, the processor is responding differently. So what can you do with that? Well, there's a couple of bytes here, and if we're probing every 8 milliseconds, it wouldn't surprise me if those were X and Y values, right? Something cumulative, total change since the last poll, something like that. You know, it wouldn't surprise me if one of these bytes maybe, or maybe even the 8.4 and 8.5 itself. Remember, the 8.4 leads to the 0.3 and the 8.5 leads to the 0.0. Maybe those clear the accumulators inside of the sensor. Seems like a thing that would be reasonable. This isn't designed to be a tape measure or some kind of totalizer, so it's going to assume that if it gave you the data and you cared about it, you kept track of it. So it's not going to build up a huge number. So 8 bits of data seems reasonable for a trackball sensor. And so you do different kinds of movements, right? And I was just kind of wiggling the trackball around here. But, oh, here's one that's interesting. 8.1, interesting. FF and 0.5. If you know your binary, and I kind of presume that anyone who's gotten this far listening to me ramble about this stuff probably knows their binary. On a signed byte, a signed integer, the top bit indicates whether it's negative or not. So FF, I doubt I overflowed the processor or overflowed the accumulator in 8 milliseconds. Seems unlikely to me. I'm not spinning this trackball with a Dremel or anything. So this is probably a negative number then. And this FF, it would be a -1. So it probably detected slight negative movement on whatever axis this is. And this 0.5 was probably slight positive movement on the other axis. So now we've got a suspicion that these 2 bytes are the ones we care about. And that is really all we need to know. And that sounds a little dismissive, perhaps, but we've got enough to build a proof of concept, right? We've got our initialization string, and we don't understand it. But it's kind of like the password to the bar, right? To the old speakeasy in the 20s. It didn't have to make sense to you, you just had to know it. So we've got our first initialization set up. And then remember we had just a little bit more initialization, maybe. Maybe it's just clearing accumulators, hard to say. But there's these other 4 bytes that we send. And then we start polling. And we know the structure of the poll. The structure of the poll is always the same. And we believe we know what these 2 bytes mean. And we kind of have ideas. Maybe the 9 here, the lower bits are representing that there's nothing to see. Because when I went through and did my survey, it's like, oh, okay, yeah, these can be all these values. C1 tends to show up when there's values set. 8.1 tended to show up when there was FB or FF, which we suspect might be a negative number, right? So maybe they're setting an additional flag to indicate that it's moving in the negative axis on one or both axes, right? But they also appear to be using signed bytes. So we can kind of ignore that. And then we've got these 2 bytes that we suspect just don't matter. So in our crass just get things working approach, that lets us build up some commands and expected responses. And I should have formatted this a little better, but these are what you'd expect, or at least what you might expect at this point. I just transcribed the data from those captures, and I made arrays of bytes. And you'll note I'm working in the Arduino IDE. I don't actually love the Arduino IDE, but it was very expeditious for me. So I've got an initialization command and an expected response. And this is more for interest than anything else. I don't actually care too much about this, but again, I am interested in what the initialization does. It just might not matter. So I built a little system that will let me send in a command with an expected response, and the response will, due to the way SPI works, the response will always be the same length as the command. And I've got my initialization and then my second initialization block. And then I've got another one for polling. And in polling, again, there's the first section that is always the same, the first 5 bytes. We expect 4 of them to always match. 1F, E0, 1D, E2. But the first one here varies. And I just kind of created a placeholder with in my system for FF, means I don't know what to expect here. But I didn't want to get a bunch of spammy logs saying, hey, I got an unexpected value. So FF indicates the expectation's unknown. Don't look for anything. And then the program itself isn't too exciting. It's kind of what you'd expect. Some helpers to print a buffer, a byte buffer that's 107 bytes long. The way the SPI library works on Arduino is that because it's reading and writing at the same time, it will read out of the buffer you get it, and then, it will transmit out of the buffer that you give it, and then receive into the same buffer. So this has to be long enough for the longest string of bytes we're going to send, which is the first initialization string, which happens to be 107 bytes. Our output will go out of it, and our input will come into it. Okay. Print buffer takes a pointer to some bytes and a length. Work intruding on life. Transfer buffer is kind of the interesting one. It takes a pointer to a byte array and a length and moves it into the buffer using memcopy. If you've written any C at any point, you may well have run into this. This takes 2 pointers and a number of bytes and moves data around. On a lot of hardware, it's very efficient, but not all the time. But it's certainly faster than looping over the array. And then calls spy.transfer, and it takes that buffer and transmits that same number of bytes back out. Validate response takes a pointer to one of these expected responses, loops over the buffer, and compares them. And again, here's the special case for the expected response being FF, -1, however you want to think of it, and ignoring those cases. But if the buffer doesn't match what's expected, then we get a printout. We just say, hey, for this position, we expected whatever was in the expected buffer, and we got whatever was in the received buffer. So those are kind of the tools we're going to use. A pretty simple set of tools, but it's enough to kind of get us moving. For SPI has a bunch of different settings, and we kind of talked about the modes, the uh, clock activity, whether clock was active low or active high, and clock polarity, and which bytes get transferred first. In every case that I've seen so far, it's most significant bits first. Sorry, bits, not bytes. And then a speed. In this case, I've slowed us right down to 500 kilohertz, half a megahertz. Since the master drives the clock, as long as you're within the parameters of the child device, it doesn't really matter how slow you go. You can go too fast. Most SPI devices I've seen do have a maximum speed associated with them. So, what do we do on boot? I'm choosing to use a Teensy. I happen to have a Teensy, I believe this is a 3.2. Just kind of, it was sitting on my desk in my piles of devices, of test devices. So I grabbed it because I knew it would be plenty fast for this. And we initialize the serial buffer because we want to get data back out of here. We want to analyze something. I delay for 1 second because it seems like the Teensy takes about a second for the serial port to stabilize. And it probably doesn't take nearly that long, but a second was not onerous, and let me move forward. And then we start configuring pins. So the first pin to configure is our slave select pin, the chip active pin for this. We look up here, I've set that to pin 10 on the Teensy. It was just a choice. There's specific SPI hardware on the Teensy, and if you've never run into the Teensy before, it comes from PJRC. There's a whole line of these, and they are really interesting little things. And I'm afraid I'm going to forget his name. It's Paul, and it starts with an S. My brain files everything by first letter. It doesn't really help. Has this entire line of these little microcontrollers, and they are amazing little boards. They have some very powerful digital signal processing on board. He does a huge amount of work to create libraries and make it work well with the Arduino IDE, which, regardless of how you feel about it, is the way a lot of people get started and is a very lightweight thing to deal with. And they are just amazing little things. And they're not even that expensive for what they are. The current version, the Teensy 4.0, is $20. And I've got one of those sitting up on the desk waiting for me to have time to solder pins to it and start playing around with it. I've got several projects that would greatly benefit from the digital signal processing capabilities of these. And they also have a little DSP workbench product that they have built that lets you drag filters together and do some really neat stuff very quickly. So, teensy digression over. Except that one of the things I wanted to show you was that if you have never seen it, there's the table of technical specifications. They also put this work into these beautiful pinout diagrams that tell you exactly what every pin is and what it's capable of. So if you have a Teensy, these are just wonderful. Sorry for the zoom in there. I'm sure there's a higher quality version somewhere on their sites, but this is what we get to see right now. So I had this up while I was writing this sketch. I picked pin 10 because it lined up well and made for a prettier breadboard. And we pick the chip select pin, we call SPI begin, and we write the pin to be 1. Chip select is active 0, remember. We call SPI begin, and we start the initialization phase. So we begin a transaction. SPI work takes place inside of a transaction, which is kind of the way it works. We set the slave select pin to 0, the chip select pin to 0, And then we call our transfer buffer helper, and we pass it the initialize command 1 and the size of the initialize command 1. How many bytes is it? And then we call validate response, and we pass it the size of the initialize response 1, and we pass it initialize response 1. And then we let the slave select pin go high. Kind of give everything a chance to breathe for a second. We begin another transaction. We set the slave select pin back to 0. We transfer a buffer. We validate the response for the second initialization. And then we end our transaction down here. And I believe this is actually a bug. There, probably, hopefully. We'll give ourselves a 5 millisecond delay in there. Now when this doesn't work in just a minute on the bench, now we'll know, well, you guys will be screaming at the screen what I've done wrong, and I will know, I will totally forget. So, anyway, we transfer the second initialization buffer, we validate the response, we set the slave select pin back high to give everything a chance to breathe, and we end the transaction. And then we enter a loop. I've put a delay of 1,000 here. Let's set the delay to something more reasonable, like 200. 200 sounds like a reasonable number. Reasonable number for unreasonable people. We begin a transaction. We digital write the slave select to 0. Yeah, I believe these are probably unnecessary. I'm going to leave those. We send the first part of the poll command, and we validate that against the poll response. And this is the part of the first 5 bytes of the poll command that, other than the first byte, we know what we expect. So we validate that response. And then we begin the second part. Again, pull the slave select pin low, chip select pin, so that it is listening to us. And we send the second part. And then we just print this buffer. We don't validate it because we don't know quite what to expect, right? But print buffer will give us the bytes just all on one line in hex. So what does this give us? Well, what am I even doing? Oop. Let's bring in the star of the show, besides Lady Ada. First, let me get the donor board here out of particular. Very So it transmitted 5 bytes. Those 5 bytes, it got back that. Transmitted 3 bytes, and then got back 1, 0, 0. Now let's see. Can you see that? If I move the trackball, data changes. One of the reasons my desk is a little bit of a mess, and I suppose I should be checking to be sure you guys can even see this. Yes, okay, good. It is in the shot. Is orienting this trackball sensor in the way that it would normally be oriented in the trackball on my desk, which is a right-handed thumb trackball, kind of led to some layout difficulties, as you can see. But actually, I can probably, well, it's not important. So we're seeing the sensor here spewing out, transmitting 5 bytes, transmitting 3 bytes. Let's turn that off. Let's turn some of the noise off. So transfer buffer. Let's just we don't need all the noise around transfer buffer. And then down here in the loop, it will only print the buffer on the second for the poles. So now interesting. What if I press? Validate response is still printing everything. That's there we go. That's what I was hoping for. So our second byte, or our second part of the poll command right now is returning 1 and 0 and 0. If I move to the left, primarily to the left, but if I move to the right, move down, primarily down. So hopefully you can see there, it took a little determining for me that the coordinate space here is actually kind of graphic coordinates, which I personally hate. So if you move up, you can see the first byte is fairly negative. F's and C's and lots of high bits being set. Move down, much smaller numbers. I said the first byte, I meant the second byte, the first data byte. So up is negative, down is positive. Left is giving us D's and E's and F's, fairly negative numbers. And right is giving us small positive numbers. So at this point, I've got an operational proof of concept with this sensor. And that is actually enough for me to call this project a fairly good success, at least at this point. What I need to do is, of course, commit these changes, push everything up to GitHub, and write some documentation and put it in the same repository in GitHub. But the repository does exist. Ben von Handorf, Logitech M570 RE for reverse engineering. Probably you knew that. I've got a directory for the traces I've captured. I've got a directory for the teensy test script I've created. And other than some documentation here, just some markdown files I need to create on how to use these things, I think I'm going to call this project pretty well completed, which is not something I get to say too often. But I've been talking for, I don't know, an hour and a bit, hour and 15, 20 minutes, rambling on. and the weather is starting to get nice outside. The sun's coming out. So I think I might call that good enough for today. I hope that this is ever useful to anyone. Hope that somebody else someday takes a look at these sensors and maybe has questions or concerns and finds this. Um, but if not, I had a good time. Oh, I should say one additional thing. It said so in my notes, but which will wind up as part of the GitHub repository. But there is a pin 7 on here that on the board had a capacitor to ground, and that seems to be absolutely required. Without that, the trackball sensor seems to lose its mind a couple of times a minute. I assume that's just like VCC stabilization or something, but I put a 104 ceramic cap in there, and that completely stabilized that problem. So I'll make sure to add that into my notes. Other than that, I hope everyone has a excellent Sunday and or whenever you're watching this. I hope that the current state of the world isn't bothering you too much, and that you and the people you know are all safe, and that you get a chance to work on something cool and stretch your mind a little bit. Maybe play with something that you don't really understand and learn something from it. Anyway, 73 to any amateur radio operators out there, and to the rest of you.